For this problem, we're trying to identify when the flare can be seen, and it helps to have the visual picture. So we're in the bottom of this gorge here. We fire a flare up, and the gorge is 244 feet deep. So after the flare goes up 244 feet, we'll be able to see it. It'll be up in the air, and then it'll start to come down, and we'll keep seeing it until it drops again down to 244 feet, and then falls back down to the ground. So what we want to plug into this equation is a height of 224 feet. We know our initial velocity is told, and our initial height is 0. We're standing on the bottom of the gorge here, so our height off the ground is 0. And so plug that in. I'm going to rearrange everything to the left side so I can easily use the quadratic formula. So add 16 squared to both sides, subtract 144t, and you get here. Now you can identify a, b, and c and plug them straight into the quadratic formula. If I ever notice that that a number can divide all three of these coefficients, I always like to make my life easier by using smaller numbers. So these are all even. They can definitely be divided by 2. Look at them a little further. You can see they all are divided by 16. They're all divisible by 16. So I'm going to go ahead and divide every single term by 16. This is what the left side changes to. 0 divided by 16 stays 0. So now I have an equivalent quadratic formula here, quadratic equation, and a, b, and c are much smaller. So let's plug a, b, and c here into the quadratic formula. And when you do that, you're going to get these results here, reduce it down, and you get to here. And then so when you add the square root of 25, which is 5, 14 divided by 2 is 7, subtract it, 4 divided by 2 is 2. So those are the 2 times when the flare is exactly 244 feet above the height of 0, above the ground. So in between those times, so greater than 2 seconds, and then up until 7 seconds, you'll be able to see the flare because it'll be above the canyon rim. To obtain the graph of this function, starting with our underlying function log 3 of x, we're going to need to refer to our translation techniques on page 271. So looking at all the different ways we can translate a graph, the negative out in front, if we take our original function and put a negative in front, it means it's reflected across the x-axis. If we add something inside the function where the x is, or subtract it, here we're subtracting 2. Subtraction means we move it that many units to the right, so we're going to move our graph 2 units to the right. And then outside the function, if we add 2, adding 2 means it's translated 2 units upward. And so here's the graph of the original function, log 3 of x. Every single point is going to undergo those translations. So just to talk about a point that has nice even numbers, 9, 2, it's going to be reflected across the x-axis. So that point's going to go to 9, negative 2. Then it's going to move 2 units to the right. So that's going to go 11, negative 2, and then 2 units up. So that's going to go 11, 0. So every point's going to go undergo those transformations. And now let's look at the graph of that transformed function, and we'll see the point 11, 0 on there. And here's what the graph of our transformed function would look like. You see 11 zeros on there, but every single point's been flipped across the x-axis, shifted 2 units right, and shifted 2 units up. For this problem, we are going to let y be cost and x be the number of satellite dishes we're making. And we're looking for a linear function. So we have 2 points here. When x is 9, we have the y value, and when x is 21, we have this y value. Use the formula for slope where you subtract the x's on top, and then in the same order subtract the x's on bottom, and you'll get 510 is the slope of the line through these 2 points. So y equals mx plus b, we know the slope is 510. Pick one of these points, and I just picked this one because the numbers are a little smaller, and plug it into this equation for x and y. And when you do that, you'll solve for b. And now that you have b, you can write the entire equation here plug in your value for m and put in the value you solved for b. Y equals mx plus b is your linear equation. We want to evaluate this sum, and since there's only 4 terms, the best approach is probably to directly just plug the values in for k. So from 2 to 5 we have 2, 3, 4, and 5, and each time just plug in what k is equal. So when k is 2, put a 2 in there and a 2 in there for k. And when you figure that out, you'll get negative 16 for 2 when k is 2, and then a 9, a negative 4, and a 1 for the remaining terms in our sum here. And when you add those all up together, you should get a positive, I'll make that a negative 10. You should get a negative 10 if you add those together. Here we're looking for a polynomial, lowest degree, only real coefficients, and it has these zeros. Now we're going to need to use the conjugates zeros theorem, which is on page 332. Basically it says if we have a complex or an imaginary zero, the conjugate of that will also be a zero. So if you're adding the imaginary part, you also have a zero where you're subtracting the imaginary part. So we are also going to have 2 minus I as a zero of our polynomial. And now to be lowest degree possible, those have to be the only zeros. And by the factor theorem, each of those zeros is going to have a factor where we do x minus the 0. So x minus 4, x minus 2 plus 1, and x minus 2 minus 1, the conjugate. So doing that complete subtraction, distributing that through, we get to this line. And I've tried to color code it through here because I'm going to multiply these 2 factors together because we're trying to expand this and get to our polynomial. And so when I take that first value x multiplied by each of these 3 terms, I get these 3 items. When I take that second value negative 2 multiplied by each of these terms, I get these 3 items. And when I finish the distribution by doing the negative I times these 3 terms, I get these 3 items. Maybe the trickiest one here is negative I times a positive I. That would be negative I squared. I squared is a negative 1, and negative of that makes it a positive 1. So now we can reduce a bunch of stuff here, combine things. Minus 2x gives you minus 4x. Plus xi minus an xi, they cancel out. Minus 2i plus 2i, those cancel out. Plus 4 plus 1, those equal 5. And now do x times everything here, and then negative 4 times everything there, and you'll get these. And again, combine things. Minus 4x squared, you get minus 8. Plus 5x plus 16x, you get plus 21. And that's everything. So that is your polynomial here. Lowest degree, only real coefficients, and we know it has these given zeros. For this problem, we're going to graph the absolute value of x, and that's made negative, so the negative absolute value of x. So in red here, I've graphed absolute value of x function. Just whatever x is, give back the absolute value. So it looks like a v here. And then the negative in front flips that over the x-axis. So it would look like this blue graph here. And you can just think of what a few values would be. If you plug a 4 in there for x, the absolute value of x is 4, and make that negative. So 4, negative 4 is a value. If you plug a negative 3 in there, the absolute value is positive 3, but then make that negative, you'd be at negative 3. So that's where we're getting these graphs. And now to talk about where it's increasing and decreasing, just look at the graph and think about moving left to right. Is the graph going up or down? So moving left to right here, I see the graph's going up, so it's increasing from negative infinity all the way up to 0. And then as I continue to move left to right, from 0 to positive infinity, we're going downward, so we're decreasing. For this problem, we're given the graph of y equals f of x, and then we want to graph this. So it's helpful to look back to all the transformations we can do on functions. This is on page 271. If we're multiplying by a number in between 0 and 1, that's going to shrink the graph down. And we're multiplying by a half, so it's going to shrink the graph. And we also have a negative in front, so that's going to flip it over the x-axis. So we're going to flip it over the x-axis and shrink it down. That's what our final result should look like. Keep that in mind as you go through it. And what you want to go through is point by point here. Look at y, because y is equal to f of x. Multiply the y value by a half and then make it negative. So the negative 4 should become negative 2 when you multiply it by a half. And then make it the opposite sign so it's a positive 2. So this point becomes this point. The same thing here. Negative 4 becomes a negative 2. Make it a positive 2. You get 3, 2. All these other points have 0 as their y value, so they're all going to have the same result. Half of 0 is still 0. Make it negative, it's still 0. So you still have 0 for the y values on those 3 points. And then connect the dots and you have your graph. And you can see it's shrunken down. It's not quite as up and down here. It's it only goes up to 2 instead of going all the way down to negative 4. So it's shrunken. And then it's also flipped across the x-axis, obviously. It's got the peaks on top here instead of looking like a W with the peaks underneath.